So this is a second part of rotation vibrational spectroscopy where we're going to go over a couple of the nuances of it. Just in a qualitative sense, we don't need to worry too much about any numbers or sticky numbers on it. This is just to let you know that it's going to be a little bit more complicated. So where did we get up to before? Well, we know what a real infrared spectrum now looks like. It's actually a little bit more complicated than simply a single peak corresponding to a vibrational transition. We have got that P branch in there, that slightly on the lower end here, and we also have the R branch, and we have a Q branch, which is sometimes missing depending on a complicated set of symmetry factors. And it's because there are transitions between rotational states that this happens. On the P branch side, everything's going down a level. That's lines going from j equals 5 to j equals 4, because delta j must be plus or minus 1. And on this side, this is going from delta g from j equals 4 to j equals 5. That's going plus 1. And you can see takes a little bit more energy to do that, so there's going to be a sequence of lines instead of a single one. And I mentioned in the last one that this is not necessarily evenly spaced. So if you did that exercise yourself to figure out what the spacing should be, you should realize that the space between those two lines should be equal to 2b, twice the rotational constant. That's because if you're jumping from one rotational level up to the next one, there's a space of 2b there additionally. The next level up or down is going to be different by twice the rotational constant. So effectively what you're looking at here is a microwave spectrum embedded into an infrared spectrum. But because we've got vibrations going on at the same time, we actually see this very irregular progression. And in this one, I think this is HCl. It's really, really pronounced. Here, look at that gap there compared to that gap there. That is a linear line in terms of wave numbers on the bottom. So that gap is 4 or 5 times larger. So that's 4 or 5 times the rotational constant versus maybe less than the rotational constant on the other side. So why is that the case? Why are these things a little bit more complicated? Well, for start, we've got an interplay between vibrations and rotations. We'll cover that. And then the consequence of anharmonicity. We're not going to do much quantum here. We're going to do it entirely as if it's classical physics. I'm not going to talk too much about energy levels. I'm just going to cover a little bit about why things may be a little bit more complicated. So we know that rotations, or rotational levels, are a function of moment of inertia, isn't it? So B, that rotational constant, is equal to, let's see if I can remember this off the top of my head, Planck's constant, 8 pi squared. Speed of light, tilde on top for centimeters, and then moment of inertia. And moment of inertia is reduced mass times the bond length squared. So here we have a bond length. The length of the molecule is now going to affect the rotation. So what does this mean? Well, if we've got a molecule that's vibrating, then the bond length is no longer constant. So if this is the bond length R, as it vibrates, it gets a bit longer. R is a bit bigger. So that means the rotational constant will change. So throughout the vibration, there's actually an interplay between these vibrations and the rotations. So R is going to change, and therefore B changes. So things are a bit more complicated. Now, quantum mechanics actually just smooth a little bit of that out, but in classical physics, it would be quite complicated. So we actually refer to this model here as a rigid rotor, or a rigid rotator. It's rigid. We assume there's no vibration. We assume in this rotational constant model here that the bond length is fixed and there's no vibrations going on, and we get that out. But in reality, there's vibrations that change it, so that B is actually going to be slightly chaotic in reality. But there is more. let's think about what happens. Why? What happens around vibration? A vibration happens around an equilibrium bond length. So this is. So this is the equilibrium bond length. Let's just call it EQ for equilibrium bond length. And then our vibration is actually about that. So it's actually the equilibrium bond length, shorter, longer, equilibrium bond length. But if we've got two atoms rotating around each other, they're spinning around like so. That's going to produce centrifugal force, or centripetal, whichever one it is, which is actually going to throw these out slightly. So you know that whole effect where you can swing things around and you feel the force trying to lengthen it. If you put these on a spring, if you literally had a spring connecting them and then span it, that spring would lengthen. There is a force applied from that rotation around the center of mass, or the center of gravity, the center of whatever this is, and it gets longer. So that means rotations actually affect the vibrations. So the rotations are going to affect that quite adversely, and the vibrations are going to affect that adversely as well. So things are actually really, really complicated there. Now let's think about what anharmonicity is. I'm going to quickly draw out the two potential wells that we'd be interested in when we're talking about vibrations here. So bond length R, and then the potential energy. In the harmonic oscillator, it's completely symmetrical. It's just a parabolic curve. In the anharmonic oscillator, there is a distinct shape to it. And here in the harmonic oscillator, this equilibrium bond length is always the same. The expected bond length, the bond length you could potentially measure here, would be the same, no matter how fast it's vibrating. You can increase, remember these are the V levels, not J's. 1, 2, 3, 4. Here, however, as they increase, don't forget they do bunch up towards the top, the equilibrium bond length begins to get longer. That's a bit more realistic. That's what you might expect. If it's vibrating a bit harder, maybe the bond length would increase. So that means the bond length is different in two different J values. So if we've got V equals 1 down here and V equals 2 up here, we have associated with this, and this is the thing that will pop up in the lab workshop practical thing where we try to calculate the bond length of HCl in a bit more detail. We have associated with it two bond lengths. One R, we'll label it R1, and R2, which should be slightly larger. That means we've actually got two different rotational constants, because follow through those equations, it means we've got two different moments of inertia. It will be slightly different. We've got all of that previous classical stuff about the interplay, but this is how we actually are going to handle it in quantum mechanics. And then, therefore, we've got two different B's. B2. So, at the different levels, there will be different values for all of these. So that changes the rotational structure slightly. They're still going to have that progression of rotational levels at both sides, but this gap in terms of absolute energies are now going to be different. And that means that the upshot of that is that basically the spectrum looks a little bit more complicated. Let's actually go back to see it now for a second. Yeah, you can see here there is this irregular progression in the size of the lines. As we get down to the P branch, the lines are getting much further apart. As we get towards the end of the R branch, they're getting closer and closer together. It's an exact consequence of this whole thing here, where we're looking at different B values in different parts. So that means you can't actually measure the rotational constant directly off those gaps. You can take an average, and it's sort of closer to the true B value near the middle, but you actually have to do something a bit more complicated. And this is what we end up doing in the lab, so I'm not going to go over it too much here. There is another lab video on it. But the idea is, if we have a look at pairs of lines that should have common states, so let me say we start on this level here. We could in theory go up a level, or we could go down a level. So we could find those two pairs of lines on the actual spectrum itself, one in the P branch, one in the R branch. So you need to find two that all have the same ground state here, and the difference is only B2 here, the upper state's rotational constant. So I should probably put the visualizer back on for that. So up here, the distance is only one of them because we've cancelled it out here. We could do the opposite way. We could just say, let's pick a common upper state, and then where would it be in the ground state? It could be 1, 2, 3, 1, 2, 3. It could be that one, or it could be that one. So our difference is only B1, the slower one. So that's how we would then deal with it. We're going to do that one in the lab in detail, and you're going to actually throw the numbers in. So this is just to warn you that that's coming up. There is another pre-lab video covering it that you can watch as well. That goes into it and probably explains it a little bit better because I've put a bit more thought into it. But that's the basics of rotational vibrational spectroscopy. And the bit that comes after this will be how do we combine this with electronic spectroscopy, which is another type of fine structure that we can deal with.